Hi, this is Hyoseok at Posttech. I'm excited to present our work zero-shot depth completion via test time alignment with affine-invariant depth prior at AAAI 2025. This is joint work with Kyungsun Kim and Byung-gi Kwon and Tae-Hyun Oh. In practical scenarios, depth information is usually obtained like these ways. First, using long-range sensors such as LiDAR or algorithmic techniques such as SLAM or visual odometry. However, depth data obtained from this method is typically sparse. These are only covers 0.1% to 10% of the total pixels in an image. Sparse depth map pose a serious risk in systems that rely on precise depth information, such as robotics and autonomous vehicles. This makes depth completion the task of estimating dense depth map from sparse depth input a crucial problem to solve. Depth compression is an epoch problem requiring prior knowledge to estimate high-dimensional variables from low-dimensional measurements. Recent methods address this by training neural networks on paired dataset of RGB image, sparse depth input, and dense depth map. To practically utilize a depth compression model in real-world scenarios, it must possess a crucial property, generalizability. But the question is, do existing methods truly achieve this? Let's see the outputs. What you see here are estimated using supervised and unsupervised approaches. Note that these models fail to generalize in out-of-domain scenarios. This limitation arises because previous methods heavily depend on pair training data, which are difficult to generalize to unseen environments. This highlights the need for a more robust and adaptive approach. Therefore, our work aims to address these challenges by developing a generalizable depth compression method that operates in a zero-shot manner. Our key idea is to align the depth foundation models of affine-invariant depth prior with matrix-scale sparse depth measurements to complete dense depth map. More specifically, building on previous affinity-based intuition, we leverage the accurate depth affinity of sparse depths as a guidance to align the relative depth affinity of the depth prior. This alignment allows us to effectively complete a matrix-scale dense depth map. In recent years, monocular depth estimation has gained attention. Specifically, recent methods leverage pre-trained image diffusion models to estimate affine-invariant depths, showing impressive generalizability and high quality even on unseen images. However, monocular depth estimation has a key limitation: scale ambiguity. So, depth compression methods provide accurate matrix-scale information, but monocular depth estimation methods have scale ambiguity. However, depth compression methods suffer from limited generalizability and quality, while monocular depth estimation shows high-quality generalizable affine-invariant depths. Motivated by this trade-off, we propose a novel approach that leverages monocular depth prior to achieve generalizable matrix-scale depth completion. But how do we effectively leverage the monocular affine-invariant depth prior for depth completion? To leverage this prior for alignment, we formulate depth completion as an inverse problem, where the goal is to reconstruct unknown dense depth x from observed sparse depth measurements y. In mathematical terms, it is written as ax equals y, where a is a forward measurement operator. Solving this inverse problem involves estimating the posterior probability px given y. In other words, estimate unknown x from measurements y. This posterior can be decomposed into likelihood and prior terms by Bayes' rule. A common approach to solving this inverse problem is through gradient descent, where we estimate the gradient of log posterior px given y. Then this gradient is decomposed into two parts. First, the gradient of log likelihood, which ensures consistency with the measurement. Second, the gradient of log prior, which acts as the score function of the data distribution. Diffusion models are modeling data distributions by estimating a score function representing the gradient of the log density, which is same with the previous slide's second term. In our problem, the signal is depth. Therefore, depth diffusion model can serve as depth prior, leveraging solution to be dense and well-structured depth map. By using the score from the depth diffusion model's output, we can compute the gradient of the log posterior. During the reverse sampling process in the depth diffusion model, we incorporate a measurement consistency term. This allows us to sparse depth measurement y as a guidance to align the affine-invariant depth prior with matrix-scale measurements, enabling depth completion. However, this soft guidance and stochastic nature of diffusion models can sometimes lead to undesirable solutions. To address this, we propose a test-time alignment method that includes a correction step. This step imposes measurements as hard constraint, ensuring that the solution remains accurate and desirable. Our test-time alignment process utilizes an affine-invariant depth diffusion model to align depth estimation with sparse depth measurement. First, at the intermediate state, during reverse sampling process, we estimate the clean depth latent Z0, Zt using the 3D formula. Next, we optimize the clean depth latent Z0, Zt guided by sparse depth measurement to obtain Z0, Zt hat. In this step, through an optimization loop, we enforce hard constraints to ensure measurement consistency. Then, the measurement consistent latent Z0, Zt hat is remapped to an intermediate latent state Zt hat to ensure the correct noise level. This step is adding noise at the proper scale referred to as resample. In summary, our test-time alignment process enforces hard constraints and consists of two key steps, the optimization loop and resampling. As a result, by aligning with sparse metric depths in complex scenes, our method ensures a desirable solution. The test-time alignment process makes metric scale depth maps closely approximate ground truth. Our zero-shot depth compression method aligns depth priors with sparse depth measurement during test time. This video demonstrates the alignment process, showing how it effectively reconstructs detailed 3D scenes. Similarly, it performs well in outdoor scenarios, maintaining high-quality results. As noted at problem definition, our main problem is generalizability in depth completion. To evaluate the generalizability of our method, we compared it with test-time adaptation method in depth completion, including pre-trained models adapted to specific domain data sequences at test time. Both our method and test-time adaptation approaches operate at test time and use only sparse depth supervision. However, unlike test-time adaptation methods that rely on pre-trained metric scale depth completion models, our approach uses a monocular depth estimation model trained only on relative scales and shifts, making it a more challenging setup. We evaluated our performance on diverse unseen indoor and outdoor benchmarks. Despite the more challenging setup, our method achieved the best results across most benchmarks, demonstrating that just aligning a well-trained monocular depth model with sparse measurements can achieve domain generalizable depth completion without requiring matrix scale training data. As qualitative results in indoor scenarios, since our approach leverages the depth prior's high-quality depth estimation capabilities, it captures scene details much more effectively than previous methods. In outdoor settings, it also accurately predicts fine details such as traffic signs and vehicles, outperforming test-time adaptation method. In conclusion, we tackled the challenge of generalizability in depth completion for practical applications. By introducing a novel and straightforward approach aligning affine-invariant depth diffusion prior with sparse measurement, our method demonstrates that aligning depth prior with measurement is an effective strategy for achieving zero-shot generalization in depth completion. By formulating depth completion as an inverse problem, we leverage the generalizability of depth prior and propose a hard constraint method to ensure accurate and reliable results. Our prior-based alignment process significantly enhances generalizability and delivers high-quality depth completion across diverse scenarios. With the introduction of this zero-shot approach, we conducted extensive evaluations across various domains, including both indoor and outdoor environments, validating its effectiveness. Thank you for listening.